So, in a minute, I'm going to stop collecting your answers. In the meantime, that's exam number 2. That means after the exam, these people have never been in this room, which means, well, what should they get for the attendance number 3? Oh. So this is a visual illustration to this question. Question? Timer? Illustration to the question? The timer again. That's yours if you want to. Free. Let's see. So, well, it depends on how we define average. And in mathematics, the average is this. So the average velocity, first of all, velocity is a vector, is equal to, now we have 10 to 23rd molecules. So strictly speaking, I would have to draw 10 to 23rd arrows. Each would represent a velocity of individual particle. This plus 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 this. So 10 to, that would take, even if a half of a second per arrow, so a half of 10 to the 23rd seconds divided by 60 minutes, divided by 60 hours. We can't spend so much time on this, so use your imagination. Here, where you have to use your imagination, etc. Okay? All right. So let's try again. Yes. So the reasoning strategy doesn't depend on the question, doesn't depend on the problem. It depends only on, well, what? The subject. Mechanics, in physics, chemistry, biology, literature, they have different strategies. In physics, the strategy always the same. Start from a definition. You have to know the exact definition of every important variable in this situation. That's velocity. And we talk about a random motion when all particles randomly move in all possible directions. So if you have, on average, billion particles moving to the left, that means on average billion particles moving to the right. If a billion particles moving up, that means a billion particles moving down. So if they all travel in opposite directions, well, that is a better. So some people changed their mind to the better. Some people changed their mind to the worse, but changing mind is better. All right? So, and in this situation, because for any arrow, there is another arrow which cancels it out. For any of those billion particles, velocity from one motion getting canceled by velocity from other, the average velocity equals 0. So don't be confused with the question about average speed. Speed is the magnitude. Speed, of course, always positive or 0, but if you add many, many positive numbers, the average speed would not be 0. So, and of course, if I ask you about kinetic energy in this situation, your answer would be always positive, depending on temperature, but always positive. Because when we're adding positive numbers, and m is positive, speed squared is positive for each individual particle. So when we add them up, we still end up with a positive number. And now, based on this conclusion, finally, we make an official definition of temperature. And not Fahrenheit temperature, not Celsius, the absolute temperature. This is an official definition. So because each particle travels in space, in general, as we know, it might rotate. So in general, every particle travels, makes translational motion, and rotates, rotational motion. So here, we don't care about rotation. We just consider translational motion as a whole. And if we have the average kinetic energy of translational motion multiplied by 2/3 and then divided by this specific number, that's what we call the absolute temperature. But of course, we don't write it like that. It's just not beautiful enough, yeah. What is it? So we just rearrange it. So again, this expression is an official definition of what we call the absolute temperature, which we measure in Kelvin. So you see, because kinetic energy never negative, absolute temperature never negative, 0 absolute temperature would mean no kinetic energy. Well, from classical point of view, that could have happened, but quantum mechanics tells that actually can't happen. Even at 0 temperature, there is some quantum motion, but we're not going to talk about that. This number, which we use for this definition, has a name, the Boltzmann Constant. That's it. This slide we've seen probably 3 or 4 times before. It's about pressure. We know that the pressure is the result of particles hitting a wall. Each particle, when it hits the wall, provides a certain amount of impulse. So we can use simple mechanics if we want to, and we can actually calculate how much force on average this wall experiences from particles hitting it every second. And from here, so there's like 5 or 6 lines missing, mathematical lines. We don't need to know. That's going to be the result, because pressure is just force divided by area. Turns out that for an ideal gas, the pressure is directly proportional to the average translational kinetic energy of a single molecule. So if they travel faster, kinetic energy goes up, they exert higher pressure, because if they travel fast, they provide more hits per second per square meter. But if they travel slower, in that case, the gas provides lower pressure. If they don't travel at all, they don't move, they don't hit, there is no pressure. And now we can combine this expression, which is a definition for absolute temperature, with this expression, which has been derived from Newton's second law applied to a bunch of particles hitting a wall. And if we combine them together, this equation now relates properties of an ideal gas. An ideal gas, that's an abstraction. An ideal gas doesn't exist, of course. An ideal gas means particles don't interact unless they collide, so only collision matters. So they all travel randomly on all possible directions. But that's a good approximation. So the air in this room is almost very close to ideal. This equation breaks only when we start reaching relatively high densities of gas. If it's a not very dense gas, it works pretty good. You've seen it in chemistry. So this relates the pressure in a gas, the volume of the gas, the absolute temperature of the gas. This is how many particles, how many molecules in a gas. That's the Boltzmann constant. That's it. And of course, we can make another step. The number of particles divided by the Avogadro number gives us this variable, which we call the number of moles. That's how we measure the amount of matter in chemistry, moles. 1 mole, 2 moles, 3 moles. So we can rewrite the ideal gas law in a different form. So this constant, universal gas constant, is just a product of two other constants. So if we multiply 6.22 times 10 to the 23rd and 1.38 times 10 to the negative 23rd, that's the result. So that's my next question. First of all, I have to close this. Oops. How do I do that? Yep. Now I gotta start collecting your responses. Now I'm gonna start the timer. And now I'm gonna switch. Yeah, I don't remember the answers here. So, question? No, it has to be right here. You should file a complaint to the IT personnel if something is not aligned properly. So this expression relates most important variables: pressure, volume, temperature. Yes. And normally, for each simple situation, one of these variables remains constant. In that case, there is a process which has a name. This process So if we look closely, we can see a syringe. So this is the volume. This is a manometer. It measures pressure. If I slowly decrease the volume push on the syringe, we can see that the pressure goes up. If my volume is a half of the initial, my pressure is twice of the initial. This process happens, well, volume changes, pressure changes. What doesn't change? Temperature. If I do it very slowly, if I don't rub it with my hand, the temperature is just room temperature, remains constant. So this process has a name, the isothermal. Iso from Greek, constant. Isothermal process. There is another process. That's a hot water. So if I, probably too much, okay. If I place this ball, this sphere into the hot water, the temperature inside this water will be going up. Yeah, too much. Now you should start thinking, what kind of a process is that? What remains constant? Temperature goes up because the temperature of the air inside this sphere was room temperature, about 20 degrees, and now it's going up. And here, where is it? Here, you can read the pressure. And if you wait long enough, you can see the reading changes. It was initially 15, now it's about 16, 17. So when temperature goes up, the pressure goes up. What doesn't change? Well, of course, the volume of this sphere practically constant. So when the volume doesn't change, the process like that has a name, isobaric process. Well, you should know it from chemistry, but still. And the last remaining process is isobaric process. Yep. When pressure doesn't change. Actually, I need this again. When pressure doesn't change, so look at this equation. If the pressure is constant, so the change in the volume is proportional to the change in the temperature. Temperature goes up, volume goes up. Temperature goes down, volume goes down. So let's see. Hot water. Well, see, it's movable. Let's hope water is hot enough. Yeah. Now, how do I know that the pressure remains constant? Well, the new equilibrium is reached every time when the force due to pressure from inside of the cylinder getting cancelled with the force of gravity. Force of gravity is the same. The mass of this system is constant. So every time when it reaches new equilibrium related to the new temperature, the pressure reaches the original value. So this is basically isobaric process. That's how it looks like. So now you have mental image of all three processes, and you will never forget it. And those are your answers. Let's see. Number 3 is the most popular. That's a wrong answer. Well, if the question is about this expression, first we have to solve the law for this expression. PV equals nRT. That's how we read it. So PV over T equals N times R. That's constant. But this is what? That's the number of moles, the number of particles over the Avogadro number. Or how else in chemistry can you calculate the number of moles? Exactly. The mass of this gas divided by the molar mass. Where do we get the molar mass? The periodic table. So you may want to refresh that knowledge, how to get the molar mass. of a gas if you know its name, hydrogen, oxygen. So, and is it constant? It depends. In this experiment, of course, the number of air inside this stays the same. It doesn't change. How can I change it? Well, I could drill a hole and add some extra air. So we need to know oh, it has a hole in it. See? I've added some gas, I've changed the number of moles, I let it go, I've changed the number of moles. So when we change the number of moles, when we change the amount of gas, this changes. So this ratio is not constant. But if we don't change the number of moles, if we don't change the amount of gas, in this situation, this will be constant. So it depends. It depends. That's the answer. Sometimes yes, sometimes no. Now, for each specific process, we can provide a graph. The most common set of axes is pressure and volume. It doesn't have to be that way. Sometimes it might be convenient volume and temperature or pressure and temperature. But well, I would say 95% of the problems would be easier to represent if we use a graph like that. Constant pressure. Of course, if the pressure doesn't change, that's the graph for the isobaric process. Constant volume, so no matter what pressure is, the volume is the same. So this line represents the isochoric process. And the isothermal process, that's a hyperbola like that. If we increase the volume, we decrease the pressure. If we decrease the volume, we increase the pressure. So we can go both ways. What is happening to the temperature? Nothing. It's isothermal process. Temperature remains the same. But if I want to compare two different isothermal processes, let's say this is one and that's another one. Which line would represent the process at a higher temperature or at the lower temperature? Well, the equation, okay, P will be equal to nRT divided by V. So this constant depends on the temperature. For the process with a higher temperature, this line lies higher, shifts up. That's it. Now, so time to solve a problem. So I'm not going to ask you this question. I've already asked you. An ideal gas in a container. Well, this is a common situation when change is happening. When change is happening, we have to divide the time into two parts. Before the change had happened and after. Before, after. It's like before the elections and after the elections. In real life, not every time matters, but in physics it does. So we have to be very careful. So initial temperature, 127 degrees of Celsius. What's wrong about it? The equation PV nRT implies we have to use the absolute temperature. We must use kelvins. So we have to convert it. That's going to be initial. 127 plus 273, 400, right? Kelvins. Now, find the new temperature if the volume was tripled. Okay. How do we call this process, what I'm doing right now? When I read, and then I write something algebraically. How do we call it? Translation. So we need to translate. So the final volume is 3 times of the initial. That's what tripled means. The pressure was decreased to the half of the initial. final pressure is 1/2 of the initial, and the quarter of the gas was lost to the environment. So final equals 1/4 of the initial. Yes, no, 30 seconds. I should set it to 30. Well, you do know now, after 33 lectures, that yes means yes, I agree with everything. No means I disagree with something. So you have like 2 more seconds to think and 2 more seconds to press. Well, again, what happened? It doesn't like you today, or me, I don't know. Well, the right answer is no. Of course, that last expression is wrong, because if you lost a quarter, you need to relate how much left, because what's lost, we don't care about anymore. It's not inside your vessel. It's not the gas, property of which we now study. It's lost. What we need is how much left inside. So the final amount of gas left inside will be 3/4 of the initial. So 1/4 was lost, which means 3/4 are left. That's our equation. Well, the rest is very simple now. So we just have to write this equation twice. 1, 1, 1, 1. 2, 2, 2, 2. And the easiest way, just do division to both sides. So hence P1, V1, N1, T1. I don't even bother to write R, it cancels. Gonna be divided by what? Well, P2 final is 1/2 of P1. V2 final is 3 of initial. And here we have 3/4 of the initial. And T final is the temperature we are looking for. That's it. All these variables getting canceled. So what's left? T final will be equal to T initial times 4/3 times 3/2. No, divided by 3/2. Yep. So 400 times 8/9. Right? So that goes over here, 4/3. That stays here, divided, so 2. That's it. Well, Kelvin. Sometimes we might need to enter the final answer in Celsius. So in that case, we shouldn't forget to subtract to 73 again. Any questions? Please just raise your hand. Now, the variable this we used for definition of temperature or to relate with the pressure was average kinetic energy of a translational motion of a single molecule. But different molecules have different shapes and sizes. So if we have a monatomic gas like helium, in that case, it has no rotational energy at all. All energy is just its translational energy. So if we take the energy, kinetic energy of a single atom, and we multiply by the number of atoms. That gives the energy of the gas. We call it the internal energy because it's inside. So in this situation, for a monatomic gas, the expression for the internal energy equals this 3 over 2 n times number of molecules times K, Boltzmann constant, times temperature. What if we have, and of course, we can rewrite the same expression using the number of moles, universal gas constant, absolute temperature. So this is the expression for the internal energy of the monatomic gas. But if we have a diatomic gas, in addition to translational motion, it also might rotate about two axes, independent. Rotation about this axis doesn't matter at all. So in that situation, we have to add rotational kinetic energy, like we did before for a rolling wheel. So in this situation, the total energy of the gas, including the rotational energy of each molecule, will be equal to this. This number 5 comes from 3 directions for translational motion and 2 independent axes for rotational motion. What if we have a complicated molecule? In that case, still it might travel independently in 3 directions, x, y, z, plus it might rotate independently about 3 different axes. So in this situation, 3 motions like that, plus 3 rotational motions, we get this expression for the internal energy of the gas. This number, 3 for a monatomic gas, 5 for a diatomic gas, 6 for a polyatomic gas, has a name. What's the name? Degrees of freedom. So in general, we can combine all 3 expressions in one. If you know everything, you don't have to take this course, right? So this is the expression for the internal energy of the gas. This number, the number of degrees of freedom, depends on the structure of the gas molecules. If it's a just single atom, it equals to 3. If it's a H2, a diatomic gas, this number equals to 5. CO2, 6. That's it. Well, we'll read and we'll look for information important. Hydrogen, H2. So it's a diatomic gas. This should be equal to 5. This is 8.31. Room temperature. The room temperature is about 20 degrees of Celsius, but we can't use Celsius, so we have to add to 73. And the number of moles, well, as we know, that has to be equal to the mass of the gas divided by the molar mass. So what is the mass of the gas? 1 kilogram. What is the molar mass of the hydrogen? Oops. Well, okay. You finished at home. It just switched. I didn't do anything. So it's meant to be. All you have to do, just refresh at home this number. I'm not going to tell it. That's chemistry. So now, as we know, we can rewrite any equation we use in terms of Boltzmann constant or in terms of universal gas constant. So this is an equation for the internal energy in terms of universal gas constant, which we just used. And if you look at the ideal gas law, you see this product, nRT. nRT is the same. So if we combine these two expressions, we can use another third expression for the internal energy, which sometimes the most convenient one. This is the question I want to ask you. I'll close this. Start again. Start the timer. Kill the time. Calculate the change in the internal energy of a hydrogen gas that expands from an initial volume. Actually, I'm going to pause for a moment. So you can keep thinking about this. That's your problem. Okay? I'm going to solve a different problem. So let's do multitasking. This is your problem. Keep pressing. This is a problem I want to solve. What's the difference? This is happening at constant temperature. This is happening at constant pressure. So that's not my problem. That's yours. Okay? Keep pressing. These are your possible answers for this problem. Now, change in the internal energy. Well, first of all, internal energy equals this, or equals this. So we always have to make a choice. What equation do we want to use? Technically, it doesn't matter. It just one would give the answer faster depending on the conditions in the problem. That's it. So here, what I read is volume, pressure. So that is a clue to me. So I want to use this equation. If I want to calculate the change, change always means final value minus initial value. So that's hydrogen, again, 5 divided by 2. Final pressure, final volume, minus 5 divided by 2. Initial pressure, initial volume. I could have do it differently. 5 divided by 2 and RT final minus 5 divided by 2 and RT initial. But I would need to calculate first the amount of gas, the number of moles. So, and temperatures. So let's see, 5 divided by 2, pressure, final pressure. Can you tell me the number for the final pressure? Someone has to say a number. Any number will do. Imagine I'm walking around and I'm looking in your eyes and asking, what's the pressure? What did you say? 300, exactly. Because it's constant. So it's the same as the initial one. 300 what? Kilo, we can't use, we have to write now. And the final volume is 7 what? Liters. Minus 5 divided by 2, same pressure, but the volume was 3. Interesting enough, when we use kilopascals and liters, these factors getting canceled, you see? Which makes our calculations easier. So 5 over 2 times 300 times 7 minus 3. That's what's left. 7 minus 3 is 4. 4 divided by 2 is 2. 2 times 5 is 10. 10 times 300, 3,000 joules. That's the change. That's how much the final energy is higher than initial. Of course, we could have calculated initial and final independently. Now it's time to Okay. I don't know what it means. Probably nothing. The clue is here. If temperature is constant, there is no change in temperature, which means there is no change in the internal energy. So for the isothermal process, the energy doesn't change. That's it. Well, work. We need to do the work in our life. So when I was moving up this little car, I was, well, not myself, but the gas inside this bottle was doing some work. The easiest calculation of work can be done when the pressure remains constant. In that case, as we know, because force equals pressure times area, and area constant, pressure constant, the force is constant. Force is constant. For the constant force, the work done equals force times displacement, well, times cosine of the angle. So if I was pushing up, force pushing up, displacement is up. So that's going to be equal to force times displacement. That's going to be equal to pressure times area times displacement. And that's going to be equal to the change in the volume. So the change, well, in the volume from here to here related to the amount of work done. So this is the expression for the work done when pressure remains constant. A better writing. What do we do if pressure changes? Well, the same thing we've done before many, many times. If a variable changes, in that case, we just use area. So the pressure is constant. That's the amount of pressure. That's the change in the volume. So base times height. This green rectangle, the area of this rectangle, represents the work done by the constant pressure. So if pressure changes, same reasoning tells us that the area covered by the graph is equal to the work done by the gas. Well, if volume increases, gas expands, the gas does positive work. But if gas contracts, that means we do positive work, gas does a negative work. So volume increases, work is positive by the gas. Volume decreases, the work done by the gas is negative, the work done by us is positive. If volume doesn't change, there is no work. We have to change the volume. Now, the equation at the top tells us how can we change the internal energy of the gas. What can we do? We can heat it up. In that case, molecules move faster and faster and faster and faster. Or we can, for example, compress the gas. In that case, we give less room. And molecules also, as the result, travel. Well, when we move the piston here, that wall, the piston, hits on molecules, supply extra kinetic energy, so they travel faster. In both situations, the internal energy changes. But that equation, you see, that equation is not very convenient because delta U, change internal energy of the gas, Q, the amount of heat absorbed by the gas, So those variables related to the gas. But W in that equation, the work done on the gas. So a mixture of different variables. So what do? We know that the work done on the gas related to the work done by the gas, like that, which is the opposite to each other. So we rewrite the expression, and this now is basically a law of conservation of energy, not mechanical energy. The energy, just energy, because there's heat energy, mechanical work done. So that's the law of conservation of energy written for the gas. But it has a name, the first law of thermodynamics. The amount of heat which system absorbs can be spent. How? Either on the change of the temperature changes, internal energy changes, or it might do some work. System might does work, that's it. The first law of thermodynamics. And now we've covered 99.6% of the whole theory. There's a couple of more equations which are very simple. That's for Monday. 321 joules of energy is transferred to a system consisting of 20 moles of an ideal gas. If the volume of this gas stays at constant 4 liters, calculate change in internal energy of the gas. It's about what? Is it about object attached to a spring? No. Is it about boat floating in a lake? No, it's about gas. So, what do we know about gas? This. This. And now this. And also this. Memorize these equations in one way or another, in one combination or another, solve 99.6% problems, well, left to solve, to be solved, including this one. So first of all, 321 joules of energy, that's Q. This number, 321 joules, tells us that we need to use an equation which has this variable in it. This slide provides only one equation like that. The equation which we call the first law of thermodynamics, which is a law of conservation of energy applied to a gas. Now, what are we looking for? That's what we're looking for. Change in the internal energy. So that has to be equal to Q minus work done by the gas. So 321 minus work. So now it's very clear our immediate goal is to calculate the amount of work done by the gas. So what do we know about it? Well, the work done by area, now here, the volume stays the same. What is the area of this graph? Zero. When volume doesn't change, there is no work done. That's it. We have to remember that. When the volume doesn't change, hence there is no work done. So that's the answer. Well, of course, that's a simple example. We're going to solve more and more examples, more complicated examples, but they all will be solved using this, all of them. All right, thank you very much. There is sign-in sheet right here. And don't forget, your exam is here. That means you're not. And if your exam is here, and you're not here, but your signature is here, you're cheating.
Card wasn't working. And then I tried changing the channel again, or just like resetting it to 41, and it still didn't work even though the green light showed. I want to go home, but I know I won't leave if I don't have a verdict.
There's a clicker which constantly.
Okay, it worked. Okay. I don't know what, I might have just needed to let it sit, but okay.
You should be fine now.
Okay, sounds good. Thank you.
I just wanted to double check that the final only focuses on problems from this unit, correct? But of course, like applied concepts that we should know from.
Ask me on Monday.
Okay.
In the beginning of the lecture.
Okay.